I'm going to start with a review again of sampling distributions because they're key to what we're doing today, and then go straight into confidence intervals and extend that to the t-distribution for confidence intervals. This is a little bit out of order of the way that it's done in the book. They have all about confidence intervals and hypothesis testing in chapter 4. I kind of felt like that is a couple of big concepts to try to introduce in one class. So there's really one main concept in this class, and that's the confidence intervals, and then next class. But we needed a little bit more to talk about, so we also do the t-distribution, which is not really a big conceptual leap like the confidence intervals and hypothesis testing are, and then we'll go on to hypothesis testing next class. So in the last class, or in the last recording anyways, we got into the central limit theorem, which relates the distribution of something we observe in a population to the distribution of its averages in samples. The distribution of individuals in the population, that's what we call the population distribution. So the heights of adults, if you're looking at the distribution of all individual heights, that's a population distribution, whereas a sampling distribution is where we draw samples of a given size. So you take one sample size and draw that over and over. So maybe we take n equals 10 adults, draw 10 adults, calculate their average height, and then do that over and over and get the average heights of samples of adults of size 10 adults. That's the sampling distribution. So the sampling distribution is something that you don't observe directly. Typically, you only observe one sample, but that distribution of what you would observe in the samples is the basis for confidence intervals and hypothesis testing. So you have to be able to think conceptually about what the confidence intervals hypothesis tests mean in terms of the sampling distribution, which is why we spent a whole class talking about the central limit theorem, and I'm going to review it a bit more today. So, well, the example we have on here was the serum cholesterol level of individuals, and that's this broad distribution, and then the mean serum cholesterol of samples of size 25 looks something much taller and skinnier. So the central limit theorem told us that the mean of these two distributions is the same, that the standard error of the sampling distribution was equal to the standard deviation divided by square root of n, and that for large enough n, the sampling distribution will always be normal. Those are the three parts of the central limit theorem. So once again, the first part of the central limit theorem is that the population distribution and the sampling distribution have the same mean. The second part was this relationship between the standard error of the sampling distribution and the standard deviation of the population distribution. The standard error is just a standard deviation. It's just that it relates to, we call it standard error because it relates to the sampling distribution, not to the population distribution. So it's a terminology just to avoid confusion between those two things. And then finally, that for large enough n, say approximately greater than 30, that sampling distribution will be normal no matter what the population distribution is. So as n increases, it affects the standard error. The population distribution is what it is, but the sampling distribution changes as you change the size of the samples. Importantly, the width of it narrows the more n increases. The larger your sample size, the narrower your sampling distribution. And additionally, the more it looks like a normal distribution. And I showed you that you could also apply this relationship between population standard deviation and the standard error of the sampling distribution to proportions, just using this equation, square root of p times 1 minus p, instead of just sigma. This is your approximation. The square root of p times 1 minus p is your approximation for the standard deviation of a proportion.